We now come to the theorems of Fubini and Tonelli. So these two theorems give us criteria when you can change the order of integrals when you have multiple repeated integral signs. So one can easily construct examples where this order of integration is not allowed. For example, if you take as an example where interchange of order of integration fails, so let's see. So I'll take on this Cartesian product 0 1 cross 0 1, define the following function f(x, y). This is given by y minus x over 2 minus x minus y whole cube. Now we can try to integrate 0 to 1 f(x, y dy dx. So first integrate with respect to y and then integrate the resulting function. So this is a function in x only. After integration, then you can integrate with respect to x. So the question is whether this is equal to integral with respect to x first, f(x, dy dx, and the resulting function is integrated with respect to dy. So are they equal? And the answer is no. This answer is no, because if you compute for example this one, so let's call this I1 and this I2. So if you take I1, this is equal to 0 to 1 y minus x over 2 minus x minus y whole cube dy dx, and the interior integral, if you want to compute it, 2 minus x minus y whole cube with respect to dy, this is equal to y minus 1 over 2 minus x minus y whole square from 0 to 1. And so you will get, at 1 you will get 0, so this is y equal to 1, y equal to 0. At 1 this is 0, and at 0 you will get, and if you compute this gives us 1 over 2 minus x whole squared. And now if you want to integrate 1 over 2 minus x whole squared, then one gets plus half. And similarly one can compute the other integral I2, but you will get minus half. So this is not equal to I1. So interchange of integrals, order of integration fails in this case. So the theorems of Fubini and Tonelli give you criteria when it is allowed to have this change of order of integration. This is not only for the Lebesgue measure but also for abstract measure spaces. So let's see what are first. We are going to define what are first called product measure spaces, and then we will define some product measures on those spaces. We will define what are called product measurable spaces. So we consider two measure spaces, x bx mu x and y by mu y. So these are measure spaces. So we will define the sigma algebra denoted bx cross by on x cross y. So this bx cross by is the smallest sigma algebra generated by elements of the form E cross F, Cartesian product of E and F, such that E is in Bx and F is in By. So this is the sigma algebra generated by elements of sigma algebra generated by elements of the form E cross F. Now we also use the following notations. So we denote for x in X the set Ex, which is the set of all y in Y such that X. So I am assuming here that E is a subset of, so E belongs to Bx cross By. Then we define this set Ex, which is the set of all y such that xy belongs to E. So this is called the section of E at X. Similarly, we can define Ey to be the set of all points x in X such that xy belong to E, and this is the section of E at Y. And similarly, if f from is a function on the Cartesian product S x cross y, say with real values, is Bx cross By measurable, this is a real valued measurable function, then we define the functions fx, this is from the set y to R given by fxy by definition is f of x comma y, and similarly we define fy from x to R. So this is for x in X and this is for y in Y. So fy of x x is equal to f of xy. So note that I am assuming this function to be bx cross by measurable, but I mean it's not a necessary condition. You can still define these functions even when fxy is not measurable. Similarly here, this can just be taken as a subset of x cross y in general, and one can still define these sections Ex and Ey. And similarly, we can also drop this condition, can be dropped, and one can still have functions which are defined using by fixing one of the variables and then defining it using x, using f. So we come to the first proposition concerning this product sigma algebra. So let us look at the statement of this lemma. So the first part says that if E is a measurable set in Bx cross By and the sections Ex belongs to By for all x, then the sections Ex belong to By for all x and Ey belongs to Bx for all y. Similarly, if f is Bx cross By measurable, then fx is By measurable and fy is Bx measurable for every x and y. So let's see a proof of this fact. Proof. So let me define sigma. This is the set of all, so let's say E cross E in Bx. So these are the collection of sets in Bx cross By such that Ex belongs to Bx for all x and Ey belongs to Ex belongs to By, sorry, and Ey belongs to Bx for all y in y. So we will show that sigma is a sigma algebra, and since sigma is a subcollection of Bx cross By, and this latter here is the smallest sigma algebra containing sets of the form E cross F, or rather E1 cross E2, where E1 is in Bx and E2 is in By. But now we will show that these kinds of products E1 cross E2 belong to sigma. So if E is equal to E1 cross E2 belongs to Bx cross By, then for all x in X, Ex, this is equal to simply E2. So this is fixed for all x, you will only get E2. And similarly for all y in Y, Ey is E1. And since these belong to By and Bx respectively, so here I am taking Ex, E1 is in Bx, this is in Bx, and E2 is in By. So the sections are simply the other part of the Cartesian products, and so this E belongs to this collection sigma. And since Bx cross By is the smallest sigma algebra containing the sets of this kind of forms, so this implies that sigma will be equal to Bx cross By, provided we show that sigma is a sigma algebra, right? So let's show that capital sigma is closed under finite union, countable unions, and as well as complements. So of course the empty set belongs to sigma, and all sets of the form E1 cross E2 belongs to sigma. And now we are going to show that sigma is closed under countable unions and complements. So this is quite easy, because if En are a collection of sets in sigma, then the section of the union n equal to 1 to infinity, the x section, is nothing. So this is the set of all points y in Y, such that xy belongs to the union of these Ens n equal to 1 to infinity. And so if x comma y belongs to the union, this implies that there exists some n for which x y belongs to En, which means that y belongs to En x. So it's the section of this set En, and so this implies that the union En n equal to 1 to infinity, the section of the union, is a subset of the union of the sections. And similarly, one can show the other inclusion. We can show that the union n equal to 1 to infinity En x is a subset of n equal to 1 to infinity En x. So this implies that the union n equal to 1 to infinity En x is equal to the union n equal to 1 to infinity En x. And so this implies that, so all these belong to By, and By is a sigma algebra. So this means that this is in By, and therefore this set belongs to By for all x in X. So this means that, so similarly one can do it for the Y sections. So this means that sigma is closed under countable unions. So this means that sigma is closed under countable unions. A very similar argument also shows that similarly we can also show that the section of the complement is equal to the complement of the section for all x in X, and similarly for Y. For all y in X. So this implies that sigma is also closed under complements, and these two things taken together mean that sigma is a sigma algebra, and this is what we wanted to show to have the equality sigma equals Bx cross By. And so this shows part 1. For part 2, this follows from part 1, because if you take fx inverse of a Borel set B, so let B be a Borel set in R, then fx inverse of B is f inverse B of x, and because f is measurable, this belongs to B y from part 1. So first of all, f inverse B belongs to Bx cross By, and then the x section belongs to By from the first part that we have shown, and this is for all x in X. And similarly one can do the Y version for this, and we get the result. Now let me remark that if you take x to be Rn and y to be Rm, then the product of the sigma algebras of Lebesgue measurable sets in Rn and those of Rm, this is not equal to the whole Lebesgue algebra for Rn cross Rm. Why? Because even if n equal to m equal to 1, we have elements in the product on the right hand side such that the sections don't belong to the Lebesgue algebra. So for example, we can take E, a subset of X, non-Lebesgue measurable, and take for example the set 0 in Y. So this implies that E cross 0 is not in L Rn cross L Rm, because the section at 0 does not for Y, because as let me write this as E prime. So if you take the E prime at Y equal to 0, then this is not in LRN. So these are both 1 LR, and so this is not in the product algebra, but E prime, the outer measure of E prime is 0. This means that E prime is a Lebesgue null set, and so since this is a complete measure space, E prime belongs to L R cross R. So this shows that there are plenty of other sets for the Lebesgue sigma algebra of the cross product if you compare it with the cross product of the Lebesgue algebras. So there are it's far bigger than the left hand side. On the other hand, I will prove it. I will leave it as an exercise to show that if you take the Borel sigma algebra on Rn and take the cross product with the Borel sigma algebra of Rm, then the equality holds for the Borel sigma algebra on Rn cross Rm. So this holds. So now let us look at the existence of product measures on this product space X cross Y with the product sigma algebra Bx cross By. So it says that if X Bx mu X and Y By mu Y are sigma finite measure spaces, so recall that X is sigma finite if and only if X can be written as a countable union of subsets of measurable subsets. This is Xj is in Bx for all j, such that mu x of Xj is finite for all j. Okay, so this is a sigma finite measure space, and we assume that both X and Y are sigma finite. Then there exists a unique measure mu x cross Y, it's denoted mu x cross Y, on this product sigma algebra Bx cross By, such that for any E in Bx and F in By, we have the product formula given by mu x cross Y E cross F is the product of mu x E and mu y F. So this is the product formula that we have seen for elementary measures, and it also works for Lebesgue measures, and this is the product formula here for Cartesian products, sets which are Cartesian products E cross F. So let's see how this can be proved. So the strategy, the idea is to apply the Hahn-Kolmogorov Kolmogorov extension theorem. So for this we will need two ingredients. One is a Boolean algebra and a pre-measure on that Boolean algebra. So define B naught to be subsets of the form S in X cross Y such that S is a finite union I equal to 1 to n EI cross Fi. So these are elementary product sets EI cross Fi, and then you take the finite unions of such where each EI is in Bx and Fi is in By for all I. So we define it using just as an analogy with the elementary measures. This is how we define the elementary Boolean algebra, and we use a similar approach here to define a Boolean algebra. So now we have to check, and I leave it as an exercise, that B naught is a Boolean algebra. And now once we have this Boolean algebra, by the way, this is not in general sigma algebra, as we have seen for elementary measures, elementary sets. It's not a sigma algebra, but it's nevertheless a Boolean algebra. It's closed under finite unions and relative complements. So now we need a pre-measure. Now if you take any subset S, if S is in B naught, then S can be expressed, it can be expressed as a finite disjoint union. This is that S is equal to I equal to 1 to n EI cross Fi, where the sets EI cross Fi intersection EJ cross Fj is empty if and only if I not equal to j. So this is a disjoint collection, just as we did for elementary measures. You can also do using similar techniques. You can prove that S can be decomposed in disjoint unions. So once we have disjoint unions, we can try to define a pre-measure. So let's define for S equal to I equal to 1 to n EI cross Fi a disjoint union mu x cross y of S is by definition the sum I equal to 1 to n mu x EI times mu y Fi. So this is a definition, and now we have to check a few things which I again will leave as an exercise. The first is that the definition above for mu x cross y S does not depend on the choice of disjoint unions, which means that if S is equal to I from 1 to n EI cross Fi, and it is also equal to j from 1 to n prime EJ prime cross Fj prime, both disjoint unions. So this is disjoint and this is also disjoint. Then we have that I equal to 1 to n mu x e I mu y f I is equal to j equal to 1 to n prime mu x e I e j prime multiplied by mu y f j prime. So this is the first thing one should check, that this is not dependent, the definition is unambiguous and does not depend on the choice of the decomposition of S into a disjoint union. Secondly, we should check that mu naught is a finitely additive measure. Finitely additive measure on B naught. So these two things are not so difficult to check. Just by following what we did for elementary measures, we can show these two results.